Medical physics for you.
Hello everyone. Welcome to another lecture. Today we are going to continue our discussion about the measurement of ionizing radiation. Today we are going to talk about the relationship between the dosimetric quantities that we discussed in the previous lecture. We will continue on KERMA, discuss the relation between KERMA and energy fluence, KERMA and exposure, dose and fluence, KERMA and dose. As we discussed in the previous lecture, the KERMA is the energy transferred from indirectly ionizing radiation to charged particles in the medium per unit mass. The released charged particles can spend their energy in two ways: 1. Through collision interactions resulting ionization. 2. Through radiative interactions, like Bremsstrahlung and electron-positron annihilation, resulting photons. So, the KERMA can be divided into two components, collision KERMA and radiative KERMA. If the fraction of the released charged particles that perform radiative interactions is G, then radiative KERMA equals and collision KERMA equals energy fluence and KERMA. Imagine a monoenergetic photon beam with energy fluence, psi, incidence on a material. The transferred energy from the photon to set charged particles in motion depends on the mass energy transferred coefficient. KERMA equals the incident photon energy fluence multiplied by the mass energy transferred coefficient. Applying the same concept, the collision KERMA equals the incident photon energy fluence multiplied by the mass energy absorption coefficient. That is because those electrons released due to collision KERMA will be absorbed in the medium. KERMA and exposure. As mentioned before, exposure is the amount of charges produced in air by photons. dQ is the total charge of the ions of one sign produced in air when all the produced electrons are liberated by the incident photons in air of mass dm are completely stopped in air. Because the released electrons are completely stopped, that means the exposure is related to the collision KERMA. In other words, it is related to the net energy transferred from photon to charged particles in air that will lose their energy through excitation and ionization. If the mean energy spent in dry air to form an ion pair is W, air is 33.97 electron volt per ion pair, and E is the electronic charge that equal 1.602 by 10 to minus 19 coulomb, then the W per E is the mean energy required per unit charge of ionization produced. That means, the collision KERMA for air, which is the transferred energy from incident photon beam to produce charged particles that will fully be stopped in air, equals to 33.97 multiplied by the exposure. As discussed in the previous video, the charged particle fluence is the number of particles incident on a sphere of cross-section area dA. Also, the absorbed dose is the energy impaired in the medium. The absorbed dose is depending on the number of charging particles that will lose their energy via collision. In other words, in case of charged particle equilibrium, the absorbed dose equals the electron fluence multiplied by the unrestricted mass collision stopping power of the medium at the energy of the electron. KERMA and dose. Consider a photon beam interacting with a material, which can be segmented into different depths for analysis. We will make the following assumptions. No attenuation of incident beams, the energy fluence, the energy carried by the photon beam per unit area, remains constant with depth, meaning there is no decrease in the beam's energy as it penetrates deeper into the material. Charged particle equilibrium exists. The energy transferred from the photon beam to liberate charged particles, such as electrons, occurs primarily in the first layer of the material. These charged particles then lose their energy through collisions within the material. Given these conditions, the following observations can be made. Collision KERMA, the energy transferred from the photon beam to charged particles in the initial interaction layer is termed collision KERMA. Due to the lack of attenuation, the amount of energy transferred in subsequent layers remains constant. Absorbed dose distribution, as discussed previously, the absorbed dose, the energy absorbed per unit mass of the material, does not occur exactly at the same location as where KERMA is measured. This discrepancy arises because the secondary electrons, the charged particles, have a finite range and can travel some distance before depositing their energy. First layer, in the first layer of the material, the absorbed dose is relatively low because the secondary electrons generated here have not yet lost all their energy. Subsequent layers, the absorbed dose increases in the layers below the first one as the secondary electrons deposit their energy over a finite range. Equilibrium condition, since the energy fluence remains unchanged and the condition of charged particle equilibrium is maintained, the absorbed dose does not decrease with depth. Thus, under these idealized conditions, the distribution of absorbed dose within the material reaches a stable state after the initial layers, resulting in a consistent dose that does not diminish with further depth. In reality, the incident photon beam undergoes attenuation, resulting in a decrease in energy fluence with depth. Consequently, both the number and energy of generated charged particles also decrease with depth. For simplicity, let's assume that the generated particles all move forward. As a result, the maximum collision KERMA is produced at the surface layer and then decreases with depth. When examining the absorbed dose, the electrons generated at the surface layer are more numerous and possess higher energy than those generated in subsequent layers. These higher energy electrons can travel further, depositing their energy at greater depths. For instance, consider these 10 electrons, that are generated at the first layer, losing their energy across different layers. Electrons in each subsequent layer will similarly lose their energy. This leads to an important observation: the KERMA is highest at the surface and decreases with depth. In contrast, the absorbed dose initially increases with depth, reaching a peak value before it starts to decline. This initial increase in absorbed dose is referred to as the build-up region. The point at which the absorbed dose reaches its maximum value is known as the depth of maximum dose. Beyond this point, the absorbed dose begins to decrease. This figure shows the variation of KERMA and absorbed dose with depth. The ratio between the absorbed dose and KERMA is denoted as beta. In the build-up region, beta is less than 1. At the depth of maximum dose, Dmax, beta equals 1. Beyond Dmax, beta is greater than 1. For diagnostic photon beams, Dmax is very close to the surface due to the lower energy of the photons. However, in radiotherapy, photon beams have sufficient energy to generate high-energy electrons that can travel greater distances. Consequently, Dmax occurs at a greater depth compared to diagnostic beams. This increased build-up region in radiotherapy is beneficial for sparing the skin from excessive radiation exposure, as the maximum dose is delivered deeper within the tissue. Question 1. What is the term for the number of particles pass through a finite sphere around a point? The answer is fluence. Question 2. Which term describes the energy transferred from unchanged charged particles to charged particles within a given volume? A. KERMA, B. Dose, C. Exposure, D. TERMA, E. Fluence. Answer is dose. That is all for today. Thank you for watching.